Hey guys, Vince and I are continuing on day 2 of our UK tour where we're exploring all kinds of alternative data center cooling. Today, Centersquare has graciously opened their doors and allowed us to film inside their data center. We're inside a part of it right now that's going to be expanding to new technologies, and in fact, they've even set up what they're calling their AI and Quantum Computing Center of Excellence. They've got a lot of cool stuff in there. They've got NVIDIA DGXs, HGXs. In another room behind us over here that we can't take a look at, they've got a real quantum computer. One of the only ones outside of HP or IBM to actually have a real quantum computer going on. But the real magic, what we're here for, the alternative cooling, is the ZutaCore solution. It's a two-phase solution. We've spoken with them a number of times in the past, and we've seen them in different trade shows, and we've talked with their executives. But today, we're going to do something really special. We got a stock one-use Supermicro server with a pair of 128-core Bergamos. We're going to convert it to the ZutaCore cold plates, and then we're going to run some benchmarks. And we're going to be able to show the difference of the core clocks being sustained, the temperatures of the cores, the temperature of the die, and I think there's a benchmark out there that I haven't attempted to break yet, but I might be able to break it today. We're talking about the new BBP benchmark for Y-Cruncher. So, without further ado, let's head inside, let's get this server unboxed, let's get it converted, and let's take a look and see what the ZutaCore solution's all about. All right, so we got our air stock results out of the server. We saw some pretty interesting stuff going on. The CPUs were running a little high. These air heat sinks on here are pretty small for the amount of power that we've got going through here. But we went ahead and we brought in Amar from ZutaCore. She's a sales marketing engineer?
Sales engineer.
Sales engineer? Yeah. Okay, and you put together a wonderful conversion kit for us, right?
Yeah.
So can you tell us a little bit about what we got going on there?
Yeah, of course. So these are two evaporators, two cold plates, if you will. The blue tubing is for the liquid. Liquid goes in. Mm-hmm. It goes into vapor. So we remove the heat by using the latent heat of the refrigerant.
Yep.
Vapor goes out from the red tubing. It's a bit bigger because the vapor expands. And this is what we're going to put instead of the heat sinks and the cooling method we're going to use.
Okay, so what's going on inside that cold plate though? How does it know how much fluid it needs? Is there a flow rate measurement? Is it run the CDU? What's going on there?
So each one of our evaporators has a on-demand float inside.
Okay.
So the idea is just like carburetor float, or even one you find in your toilet.
Okay.
So liquid
Let's go
goes
with
in.
carburetor.
Yeah, go with carburetor. Liquid goes in. If there is no load, the liquid fills up the evaporator. The float floats and shuts down the liquid inlet.
Okay.
Once some liquid evaporates or boils, vapor goes out, the liquid level goes down, float goes down as well, and then more liquid goes in. So this is a completely mechanical way of monitoring the amount of liquid that goes inside in order to keep the pool just enough high inside the evaporator.
So each CPU or GPU in the entire system is self-moderating its flow?
Correct. It doesn't matter what its location inside the server or inside a rack.
Okay. And then what advantages does that bring as far as the total system? Like when we start thinking about the CDU, or in your case, the heat rejection unit, right, mm-hmm. the HRU, and the manifolds that come in, what advantages does this type of system have?
So first of all, servers are not people. They don't need to remain at 25 or 30 degrees centigrade in the room. They can work at higher temperatures, and this is what we do. We're allowing to work at higher temperatures.
Yeah.
So
because you don't start hitting thermal throttle till usually like 85 or 90.
Exactly. So what we have is the thermal performance of the evaporator sets the delta between the junction temperature and the saturation temperature, so the boiling and condensing temperature.
Okay.
We can set up and play with the boiling and condensing temperature according to what the CPU needs. So mm-hmm. we would usually take the lowest junction temperature on the rack, and this is what dictates the saturation temperature or the condensing temperature for the whole rack.
Okay.
And then from there, the primary loop, which is the loop that condenses the vapor back to liquid, it can be either based on air or on water. For air, let's say for old data center infrastructure, where you have raised floor and stuff like that, yeah. It's really convenient because the HRU sits at the bottom, mm-hmm. takes the cold air right from the floor. You can reuse the heat, of course, when the water comes out from the primary.
Kind of like a traditional heat exchanger that I would see in pretty much.
Yeah, it's a plate heat
right?
exchanger
Okay.
that we're using as a condenser.
Okay.
So warm water go in, hot water go out.
Yeah.
And of course, it condenses the vapor back to liquid on the
Okay.
other side.
So what kind of pressures are running inside these tubes?
So the vapor pressure, we like it around 1 bar gauge.
Okay.
So 1 bar above atmospheric pressure. Then the liquid is always 1 bar above it.
All right, so talk to me a little bit about that liquid then. So we got to play with some earlier and I got to put my hand in it, which was really cool. It evaporated really fast and even just kind of sitting at room temperature in the small cup that we used, it was boiling off. What's going on? Like, take me from the beginning of that fluid. You guys refer to it as a refrigerant, right?
Yes, correct.
Okay, and then it evaporates obviously at room temperature. And what happens if a leak happens inside the server?
So first of all, we are using 2 different liquids, one for the CPUs, different one for the GPU systems.
Okay.
For the CPUs, we are using Opteon SF33. It boils at 33 degrees at atmospheric pressure. Mm-hmm. So of course, if you touch it, it boils right away.
Yeah.
And if it's just there, it evaporates slowly bit by bit. The other one we're using is R1233ZD. This is what we're using for GPU. It boils at 18 degrees centigrade.
Okay.
The reason we took a different refrigerant is the lower junction temperature the GPUs needs to be at. So, for example, H100, H200.
Those are hot.
Yeah, those are hot, but they need to. Their maximum junction temperature is around 80.
Yeah.
So this goes back to us, and the heat flux over there is much higher. Mm-hmm. So you even for the copper part of the cold plate, you have a bigger delta T. The condensing temperature will be lower, so around 43. And since we like the vapor pressure to be around 1 bar, we want to be 43 at 1 bar.
And then, so if it spills out onto the server, it's obviously going to evaporate. But is there anything to worry about if it's
nothing at all? It's a dielectric fluid. Both fluids are dielectric, so
completely non-conducting.
Yeah, no, nothing. Nothing will happen to the servers or the IT.
Is there any sort of losses that occur in the system? Do you have to top off the fluid or worry about maintenance like this?
Yeah, so basically it's a closed loop, but there could be some loss to the system due to maintenance of the servers themselves. So, for example, if you need to attend the server and you take it out, you put it in, you put it back in, it could have been that some liquid went out from the system when you plugged out the QDC or push it back in.
Yeah.
So you do have to fill up a little bit more liquid inside. The amount of liquid that you lose depends on the load that you put in, on the amount of cold plates you have. So,
okay.
Yeah.
Is there once, let's hypothetically, like if we had a perfect closed loop that there wasn't any leaks or anything like that, and is there any sort of aging that occurs with the fluid that I have to worry about and have it changed out? So once it's in there and it's good for forever essentially. Mm-hmm. Okay. Moving on to kind of the cold plate technology, we see, we've looked at a few different cooling techs, but this one, you guys kind of have a special trick up your sleeve as far as the amount of TDP that you can handle. Can you talk about what we're seeing as far as the ability, upper limits for GPUs, for CPUs, stuff that's around the corner? We know it's going to get pushing over 1,000 watts. Mm-hmm.
Yeah, so first of all, for us, the amount of TDP almost doesn't matter. What really matters is the amount of TDP compared to the area it's on. So the heat flux, actually. So for example, if I put 1 kilowatt on this whole table, we could cool it easily. Right. But if it's on a small chip, it's obviously much harder.
Yeah.
So for example, Sapphire Rapids is about 23 watt per square centimeter. SP5, the Genoa ones are, if I remember correctly, around 30 watt per square centimeters.
Okay.
H100 is 50, 70, depending how you look at it. We've reached not too long ago, about a month ago, over 450 watt per square centimeters.
Okay, so that's significantly higher than where the tech's at right now.
Exactly. So in terms of limits, currently there are pretty much no limits.
It's practically none at this point in time, okay.
Yeah, pretty much. And most of the CPUs, GPUs today have more than one die underneath the chip. So it's a multi-chip packaging. So for example,
these Bergamos have a lot of chiplets around them.
Yeah, exactly. So you have the I/O in the middle, and then a few CPUs on the sides.
Yep.
Each one of them has different heat fluxes. Since it's all under the same pool, basically, and all boils at the same temperature, you can show different junction temperatures under the same die without worrying about the direction of the fluid. So there is no significance to, let's say, upstream or downstream, because it's all under the same pool. So the heat goes from bottom to top and not from one side to another.
Okay, that makes sense. All right, well, let's go ahead and dig into this guy and do the conversion. Sound good?
Yeah.
All right. Yeah. So standard server service almost with the replacement of a heat sink or repasting, right? There's not much else that we have to do to it, huh?
Nothing else.
So you guys offer these, so we're doing Bergamos. These are the 128 core CPUs, but you offer heat sinks for GPUs.
Yes.
Not only the 8-way SXM stuff, but PCI card ones as well?
We're starting to get PCI cards by demand.
Okay,
it's under development and can be. We can deliver. In general, we can develop cold plates pretty fast. So it takes us around 3 months to develop a cold plate.
Oh, that's pretty quick.
So we can do anything by demand, basically.
Right now, we would have to go through like a system integrator to have this done, but the hope is in the future that you can order a server with the solution, right?
Correct.
So if I do want the ZutaCore option for my data center, how does that look like from an ordering perspective when I call up Supermicro or Dell?
It starts with the customer demand, right?
Yeah.
So if a customer demands an 8-way GPU with ZutaCore system, they can order the tray without the heat sinks from NVIDIA. So the server manufacturer actually can order the tray without the heat sinks. And then we have other companies, third-party companies that does the retrofit for us.
Okay.
For the CPUs, Boston is one of our favorite partners, of course.
Okay.
For GPUs, Boston DE is going to be certified soon to do the retrofit themselves.
And big shout out and appreciation to Boston for hosting us for this event today. They've got a whole test rack set up for us to be able to play around and hook this system up and do some testing on. So we're hoping to get some big numbers. We might even be able to pull a world record or two out.
Yeah, maybe.
How good is your cooling solution?
The cooling solution is great. Basically, it lets you work at high workloads for as long as you can, as long as you want.
So we're about 3 minutes into this, into working here, and we've got one of the heat sinks off. We've got our PCI pass-through installed. What's the average kind of retrofit time for conversion or installation?
So for each installation, what we usually do is we set up the HRU, the rec side first, with the tubing and the manifolds. Then we compress air inside to 2 bar just to test the system for pressure and make sure there are no leaks. While this is going, because we need to set it up for about 2 or 3 hours, while this is going, we're doing the server retrofitting. So the retrofit itself takes a few minutes. Before we do the actual retrofit, we do the pressure test for each server kit as well, just to make sure there are no leaks or anything like that. So it's a matter of minutes.
So talk to me a little bit about that, the leak concept, right? So if a leak does develop, you'd be able to detect that in some way?
Yeah, so let's talk about 2 different kind of leaks. So one leak is, a small leak that happens, let's say that you don't see in your eye. So it could be that it's happening, little by little. What would happen is the pump will keep pumping liquid inside, and the liquid level in the buffer will slowly go down. So the system alerts you for that. Okay. And then, of course, you can find a leak. We usually use a standard sniffer. Do you know what a sniffer is?
Yeah. So for those of you playing along at home, Vince is going to put up a little picture of a sniffer.
Yeah. So we're using a sniffer just to try to detect the leak itself. We fix the leak, so it could be just to replace the server kit itself, or it could be sometimes, just that someone didn't really plug all the way in, or plug the tubing all the way in.
All right. You want me to grab some of those?
Yeah.
Okay, we got this one. Perfect. So the trick here is just to get them kind of close, and then... Now, do these bottom out, or do these have a torque spec on them?
They have like a torque, and it's exactly like the heat sinks. Yeah.
Okay. So with these lines and stuff, so this blue one looks pretty flexible. I don't think the red one you could probably get some pretty tight radiuses out of this guy, but you would need a little more for that.
They're all pretty flexible. Like you can bend them. Of course, the 4 millimeters is a lot more flexible than the 8 millimeters.
Okay. And if I'm doing maintenance in my rack, do I have to call you to get this special tubing?
No, not at all. You can order it off the shelf.
Okay. Is there any like practical limit, or what would be like the upper limit for distance? Like if I wanted to have like a special set of like extensions to have for my crash card if I'm trying to work on a system and diagnose it, could I do something like that?
Probably like 2-3 meters. So let's say 2.
Okay, so enough to kind of right out front of the server. Right.
Yeah. So let's say 2 racks to each side would be.
Okay.
Yeah, fair.
Awesome.
Yeah.
And then where do we go from here?
Yeah. Let's take these off.
Oh, it's just a compression fitting. Very cool.
Yeah. And we can. There we go.
There we go. There we go. We're in. All right, so we got our retrofit kit all installed here. Let's take this thing to the data center and show us how we get the system ready and plug it in.
Mm-hmm.
All right, let's head out to the pod and get this thing tested and see how our performance is. All right, so we got our system all racked up here. We're inside the AI Center for Excellence, and we're about ready to hook it up for the first time to the ZutaCore manifold. So we've got our red one, which is our gas return, and our blue one, which is our fresh cool liquid supply. So they told me there's no special order to connect it in. I want to do red first just because it'll make me feel better. So you pop that on, that was easy, and then this guy doesn't need to be retained. And now the system is pressurized and connected to the loop.
So this is our SDC, software-defined cooling.
Okay.
It's basically a software to be able to monitor your data center and our systems as well.
Okay, so this is more than just your CDU. This extends beyond that.
Yes,
Okay.
correct. It also shows, you can see here, the highest temperatures of the CPU, average utilization, the power consumptions of the rack, power consumption of the CPU. And also it gives you all the HMI you can see on the small screen on the HRU.
Oh yeah, I can see we've got pressures and speeds and feeds and...
Yeah, exactly. So you see the air inlet temperature, fan speed, vapor inlet temperature and pressure, the pump power. So you can see the servers here.
Yep.
So this is each one of the servers, its power that it's taking, so currently 130 watts, 180 watts, etc.
Okay, so this is tied to the PDU as well as you build the virtual rack in there in the software so you can see where everything is. Okay.
Yeah, and also the highest junction temperature of each CPU.
Okay, and that plugs in through the IPMI of the system then? Mm-hmm. Very cool. All right, so we got our server converted over to the ZutaCore solution. We got it racked up. I got to plug in the cool fittings, but you did some fun stuff with your fancy machine down here. What happened there? What was all that about?
Yeah, so basically every time you push a server into the manifold or into the system, we also push some air into the system. We want to purge this air out. This is one of the reasons we have this service unit. It's not that fancy, it's pretty simple. It just has a pump, a buffer, a small radiator with a fan as a condenser.
Okay.
And what I did is after you turned on the stress test, in order for some boiling to occur, so we're basically trying to push the air into the buffer. Then we're purging the air out into the system and then into the buffer, into the refrigerant tank.
Okay.
So that no vapor and liquid will go into the atmosphere or anything like that.
Awesome. Well, let's go hit this thing with some load and see what we can do with it.
Yeah.
All right. All right, so we got the server all powered up, hooked up. They've purged the system. The engineers are currently doing the final checks to make sure everything's in balance. We've had to do it a little more because we've been doing so much unplugging and replugging of things. But I've got Cinebench 23 running here. We're putting up scores of about 120,000, but I think the most impressive thing is looking at our specs and hardware info while this thing is running, our CPU average temperature is only sitting about 80 degrees under full load, which means that the CPU can maintain full turbo as long as that temperature is maintained. Where you start getting in trouble, especially with air systems, and you start taking performance hits, is when that CPU temperature climbs up a little bit higher and the CPU needs to throttle and pull power back in order to maintain the temperature. But thanks to the ZutaCore two-phase solution that we've installed in here, it's never really going to get much above that 80 degree, even under full load, looping Cinebench over and over, so it can maintain the highest possible clock rates. Let's hit this thing a little bit harder and see what we can do to it. All right, so we broke out the Y-Cruncher BBP benchmark. This is currently in beta on HardwareBot, and we're going to go ahead and do 1 trillion digits of pi computation. This should take a little bit of time. We're not in this one for a speed run necessarily. We're in this to load this thing up with a constant hard load that's just going to stress the CPUs and get them to the absolute max. So currently we're hitting 214 watts per CPU, and our temperatures, our average across the die is actually 69.1 degrees Celsius. And again, this is absolutely pegged. Let me pull up Task Manager here so you can get a good view. 256 cores, absolutely maxed out. We're actually turboing right now over the base frequency with all cores under 100% load. Again, this is SMT disabled, and it is just 100% maxing out the BVP computation formula to do 1 trillion digits of pi. So we're gonna try for a world record here. I think we can do it. The current world record is from a friend of the channel, Sebi. He's got 12 seconds, 451 milliseconds for the 100 billion pi BVP run. So let's go ahead and kick this off here, 100 billion digits. This is Benchmate, we've got HPAD enabled. We did turn off SMT, not DRAM limited at all. So survey says 10.284 seconds. The current world record is 12.45, so we beat it by 2.2 seconds. All right, so the next one we're gonna go after is the 10 billion. I know I don't stand a chance in the 1 billion because I just don't have the clock, but I think I have the core and I think I have the cooling to go after the 10 billion. Current record, 1 second, 162 milliseconds. Ready, set, go. There we go, that was the world record. 145 versus 162. What a day we've had here at the Centersquare Data Center here in Reading in the UK. Vince and I have had an absolute blast learning all about the ZutaCore solution. Big thanks to Boston Limited for setting this whole thing up and allowing us to convert one of their servers over to the ZutaCore solution. We learned so much about both the fluid and how the whole system works. I got to hold some of the fluid in my hand, I got to touch it, I got to feel it. It doesn't leave any stink, any residue or anything like that on your fingers. And it's dielectric, so if there's any sort of leak or spill, it's not gonna short out a server, it's not gonna cause any problems. With those AMD EPYC Bergamo CPUs, we were able to set 2 world records today on the ZutaCore solution, a first of its kind submission to HardwareBot. If you like what you saw here, make sure you like and subscribe. And if you have any questions about what we did here, what you saw here today, feel free to jump into our Discord. I'll be there. I'll be able to answer any questions about what we did. For now, that's all. We'll see you around.